Thank you for the introduction, and I would also like to thank the organizers for giving me this opportunity to speak here in the trimester program. So when I was a graduate student at Bonn, I actually participated in the first trimester program. It was the summer of 2014, about the first trimester program of harmonic analysis in the summer of 2014 that Herbert Koch and Christoph Thiele organized. Okay, cool. The title of my talk today is some recent progress on the Bochner Riesz problem, and this is a joint work with Changgen Oh, my graduate student at Madison, Shukun Wu. I think right now we should say that he's a former student at the UIUC and now is a postdoc at Caltech, and Hong, Wang, and Rishan. Okay, cool. So let me first state the problem. Let's fix alpha bigger than or equal to 0, and we define the Bochner Riesz multiplier to be the following. It's defined to be 1 minus modulus c squared to the power alpha. Let me explain what this plus means. Plus just means this function is equal to 1 minus c squared if it is smaller than or equal to, well, let's say c is smaller than or equal to 1 and it is 0 elsewhere. This is our Bochner Riesz multiplier, and we define the Bochner Riesz operator to be just the multiplier transform of the Bochner Riesz multiplier. Okay, just introduce as few symbols as possible, I suppose. E to 2 pi I. M alpha C. So this is, we first take the Fourier transform of F multiplied by the Bochner Riesz multiplier and then take inverse transform. And we would like to study LP bounds of the Bochner Riesz operator. Okay, and the Bochner Riesz conjecture says the following. It states that, let's say that we are in dimension n bigger than or equal to 2, and for an exponent p, this is the exponent. If you haven't seen this exponent, this is, I suppose, the most important exponent in my talk. And please remember this exponent. And for simplicity, you can think of the case n equals 3, and p is bigger than or equal to 3. It holds that the okay, I think it's easier to give names, I guess. Then we know that the conjecture says that the operator, Bochner Riesz operator, is bounded on LP depending on alpha n and p. Whenever alpha is bigger than, of course, if alpha is extremely large, that means our operator is smooth, and it would be easy to prove a boundedness. And the Bochner Riesz conjecture says that if alpha is bigger than this exponent, then the Bochner Riesz operator is bounded on LP. If you didn't see this conjecture before, and well, if you don't like remembering too many exponents, then you don't need to remember this one. And what you need to remember is, again, this p bigger than 2n over n minus 1. And in the endpoint case, in the case 2n over n minus 1, we have that alpha is bigger than 0. Okay. So this is the endpoint case, and by interpolation, it implies everything else. Okay, cool. So this is the Bochner Riesz conjecture. And we have a closely related conjecture, which is the restriction conjecture. And this conjecture, there are different ways of writing this conjecture. Let's write the one form of it. S minus 1 is the unit sphere in Rn. And let d sigma denote the surface measure of the unit sphere. And we take a function, L infinity function, defined on the unit sphere. We define the Fourier transform of this measure supported on the a singular measure, a measure that is supported on some subspace. Define f d sigma hat. This is a Fourier transform. I d sigma. So this is the Fourier transform with x being a vector in Rn. Okay, cool. And the Fourier restriction conjecture says that this conjecture says that the Fourier transform of the measure LP norm is bounded, again depending on all the parameters n and p. D sigma whenever p is bigger than the same exponent 2n over n minus 1. Okay. And this is just one form of the restriction conjecture. And one can also, for instance, by using factorization theory of negation and Pcia, and formulate other equivalent or almost equivalent versions of the restriction conjecture. Okay, cool. These two conjectures, so related to these two conjectures, there are also Bochner Riesz problem or Bochner Riesz conjecture for paraboloids, and also restriction conjecture for paraboloids. So what are they? Bochner Riesz conjecture is that in the Bochner Riesz multiplier, we see that if we look at the level set of our multiplier, or if we look at singularities of this multiplier, we see that the singularity of this multiplier is exactly on the unit sphere as a -1. And that is why we can expect there's some connection between the Bochner Riesz conjecture and the Fourier restriction conjecture. The Bochner Riesz conjecture for paraboloids is that we define a multiplier with a singularity on, let's say, the on truncated paraboloids. And the restriction conjecture for paraboloids is that instead of taking the unit sphere, we replace it by, say, a truncated paraboloid, and we take a function L infinity function defined on this paraboloid, and then take Fourier transform, asks the same question, LP boundedness of the Fourier transform. Okay, so these are a few questions, a few conjectures. So other questions so far? Okay, cool. let me state a few known results on these conjectures. A first one is let me start with the result of Tony Cabri, and this is a result in '92 where he showed that the restriction conjecture, let's say restriction for paraboloids, it implies Bochner Riesz for paraboloids. And also later, Rogers, this is a result in 2008, used a similar method and showed that the restriction conjecture also implies local smoothing for the linear Schrodinger equation. And let me write down local smoothing estimate for the linear Schrodinger equation. For instance, let's write down a local version of it. By using Fourier transform, solve the linear Schrodinger equation. 0, and then at time t equals 0, we have initial data fx. So we have fxc I c square, and then inverse transform c deep c. So this is a solution to the linear Schrodinger equation. And by local smoothing, what we mean is if we integrate LP in Rn, and in time, we would like to bound this. Let me write a WSP norm, Sobolev norm. And for such an estimate, we call it the local smoothing estimate for the linear Schrodinger equation. And Keys showed that by using a similar argument as in the paper of Tony Cabri, showed that if we assume the Fourier restriction conjecture for the paraboloid, then he obtained sharp estimate for the local smoothing estimate for the linear Schrodinger equation. Okay, that is, determine the optimal S for every P. So both of these results used the so-called pseudo-conformal transformation. Pseudo-conformal transformation. They also use some special features of the paraboloids in order to complete squares. Something like I'm giving an much simplified version of what they did in their paper, of course. So it's something like this. If we expand the square, then we get x squared over t minus 2x inner product with y plus t y squared. Okay. And what they did is we'll see that this is this we will treat as a constant, and as it is on complex exponential, we will see that this term will have modulus 1, and for the remaining two terms, we see this is exactly a Fourier restriction problem for the paraboloids. We have an inner product structure, and this is xt, inner product with y modulus square. And this is how why they only stated their results for the paraboloids and exactly for the linear Schrodinger equation, but not any general Schrodinger equation where the phase function For instance, where the phase function can be replaced by c to the power gamma, for instance. They only did it for gamma being 2, because they need to complete squares at some point. Okay, so this is what they did in their papers. Also perhaps the main reason why they didn't claim the result that that restriction conjecture for spheres imply Bochner Riesz or local smoothing for more general Schrodinger equations. Okay, and we will see that in this talk, we will see that the completing square part is not essential. Okay, and it is the I mean in the in both the paper of Tony and the paper of Keith, the completing square part is not actually that essential, and it is use of pseudo-conformal transformation that play the magical role. Okay, and our main result states that not stated precisely. Main result is that the restriction conjecture for this sphere, it almost implies the Bochner Riesz conjecture. We would like to, of course, it would be great, and we would love to remove this almost and remove this quote mark. We are not quite able. We are not able to. And let me first explain what we mean by almost implies. It is in the sense that if we apply the after applying the pseudo-conformal transformation, which is almost the same as the pseudo-conformal transformation as in Tony and Keith's paper, we will see that all the recent tools that have been developed in to study the restriction problem, including tools including multilinear restriction estimate of BCT, Benny-Cabral, and broad narrow analysis and of Bourgain-Gu's and polynomial methods, and also decoupling inequality of polynomial Wolf axioms, and all these recent techniques, they apply equally well to the Bochner Riesz problem for spheres. And as a consequence, we proved that the Bochner Riesz conjecture holds for P, for that it is bounded on LP for the same range for P for which the restriction conjecture has been verified. Okay, and also this is explain the word "ode" from our title, the ode approach in our title. So we are using an approach that it has been in the literature for over 30 years, I suppose. Okay, so this is the main result in the paper. I would also like to mention another project, an ongoing project of, it's not a project of myself, but from an ongoing project of a related project from Shaoming Guo, from Chenggen O, and from Shukun Wu. So they are looking at local smoothing estimates for general Schrodinger equations. For instance, for equations of this form, or for fractional Schrodinger equations, inverse transform, and try to prove optimal local smoothing estimate for fractional Schrodinger equations. In their project, for some gamma, if I remember correctly, for gamma bigger than 1, then pseudo-conformal transformations are enough, and one can still apply pseudo-conformal transformations and reduce this problem to almost to the restriction conjecture. And also in many other cases, it's very interesting and actually quite surprising that pseudo-conformal transformations may not be enough and they have to do plenty of other things. Okay, this is one project they are working, and also there are a few other related operators that they are trying to think of related ones. Okay. Okay, good. Let me continue. Next, I would like to mention the result of Terry Tao. He proved that the Bochner Riesz conjecture, the Bochner Riesz conjecture for the sphere, implies the restriction for the sphere. And well, what he proved is much more general. Of course, he proved that Bochner Riesz for other smooth surfaces with positive definite form, or even Bochner or even Hermander type oscillatory integrals, if we assume some LP bounds, then they imply restriction for related surfaces. We don't need to start with not necessarily starting from the Bochner Riesz conjecture, but also some more general Hermander type oscillatory integrals. And then he, from there, he deduced the relevant restriction conjecture. And also he, Tao also mentioned in his paper that at least heuristically, so he said that the restriction problem implies the Bochner Riesz problem. Implies Bochner Riesz, and our paper just provides some further evidence for such heuristics. Okay, good. These are some results in the history on the relation between these two problems, Bochner Riesz problem and the restriction problem. Okay, let me continue with some more results, some partial progress on these two conjectures. For instance, in 2D, we know that this is a classical result of Cardigan and Schrelin. Also, there are other proofs by Hermander, and also in Pfefferman's paper, Pfefferman's thesis, I suppose. A second result is we have Stein-Thomas for the restriction problem, and Pfefferman also used the Stein-Thomas and proved Bochner Riesz conjecture for the same range of P. And then there are works of Bourgain in the early 90s on both problems, and results of Tao on Tao's bilinear argument for the restriction problem. So this is Tao's bilinear method, and Li applied the bilinear restriction of Tao and proved Bochner Riesz for the same range, and other results. Bourgain and Goose introduced broad-narrow analysis. They successfully used the multilinear restriction estimate of BCT, and then made progress on both problems. on both the restriction and the Bochner Riesz problem, and until the last result is the free restriction problem. I would like to mention is by Guos, and also for the Bochner Riesz problem, as a result of GHI, Guos, Hickman. Yeah, so it would be awkward to spell your name wrong, Marina. And they used polynomial method and gave a complete answer to Hermander's conjecture, and as a consequence, they proved Bochner Riesz conjecture in a wider range. Okay, so this is a review. It's not a complete review. I just mentioned a few. Well, not even all the one that we rely on, but for the sake of time, let me only mention these results. The one that I would like to say a bit more is this result. In most of the previous works, for instance, in the work of Guos, Hickman, and the Ilopolo, the way that we look at the Bochner Riesz operator is to view it as a Hermander type oscillatory integral. For instance, let's define it as lambda is a large parameter, x, omega. We have our amplitude, omega, x is in Rn, and this to view Bochner Riesz operator as a Hermander type oscillatory, or to view it as this type of oscillatory integrals, satisfying some non-degenerate condition, and also some positive definite condition. For instance, perhaps a most interesting example is we write this as x prime omega plus xn omega square, where x is equal to x prime xn, and x prime is x1 xn minus 1. And if we take such a phase function, then what we see is exactly the Fourier extension problem or the Fourier restriction problem, right? And by positive definite condition, what I mean is that phase function or the quadratic surface that is determined by this phase function is non-degenerate. It has all positive principal curvatures. Okay, so there's some limit for this viewpoint. So Hermander conjectured that for elliptic phases, T lambda fx, he conjectured that if phi lambda satisfies some non-degenerate condition and also positive definite condition, then the operator T lambda is bounded on LP for the same range as in the restriction problem, 2n over n minus 1. And this was disproved by Bourgain in I think in 1991 or 1992. He disproved Hermander's conjecture by showing that some Kakeya compression phenomenon can happen for general Hermander operators. Okay, and later I will say a bit more about Kakeya compression. Okay, let's go back to the item 6. And in the work of Goose, Hickman, Iliopolo, they gave a complete answer, as I mentioned, to Hermander conjecture. They determined optimal range of LP boundedness of such operator T lambda, and Bochner Riesz operator can be viewed as a special case of this operator, and therefore this is how they proved the LP bounds of the Bochner Riesz operator in a large range. But we know now that it is not the largest possible range for the Bochner Riesz operator. Okay, the Kakeya compression. So for Kakeya compression, one simple example where Hermander's conjecture fails is this example. Is an example in R3. We have, let's say, x1, y1. Our phase function is x2, y2 plus t y square. So far, what we have written down is again exactly the Fourier restriction problem. T square. Let's put a qy, and qy is a quadratic form in y, and so as long as qy is not similar to y modulus. For instance, qy is y1 square plus 2y2 square, or basically any other form, y1, y2, or other form, as long as it is not a constant multiple of y modulus squared, then Bergen showed that Hermander's conjecture would fail for such a phase function. Conjecture fails for such a phase function. And the way he did it is to construct a family of curved tubes. The union of these tubes is very small. Let me draw it won't be a good picture. This is something like this. It's we have a family of not a family. We have curved tubes, and these tubes may also point to other directions. But the union of these curved tubes, they're all inside some let's say hypersurface. Okay. And tubes, well, for instance, the green ones and also the blue ones, they are pointing in different directions. And this is what he meant by Kakeya compression. That is, we have a number of tubes pointing in different directions. However, they can all be compressed inside a small region. And this is how he disproved Hermander's conjecture. And he actually proved that Hermander's conjecture fails generically. Okay, good. So this is what I would like to say before entering the proof of the some proofs. So may I ask whether there are questions? Okay, cool. So let me say a few words on the proof of our result. The we first do the well-known Cardassian-Schilling reduction. and we reduce our, we write, it's basically we compute the Fourier transform of the Bochner Riesz multiplier, and we write our operator. We look at the operator on the spatial side instead of on the multiplier side, and we get x minus y modulus. A is a compactly supported amplitude function, fy dy. So x is in Rn, y is in Rn. And if we compute the Fourier transform of the multiplier, then this is the operator. We see exactly a convolution operator. And for this convolution operator, we will prove the LP bounds of this operator. And now let's see how what we mean by pseudo-conformal transformation. Is it just a nonlinear change of variable? That is a very useful nonlinear change of variable. Okay, to proceed. In step one is that we will freeze one variable. For example, we will freeze lambda x minus y, and we write y as y1, yn minus 1, yn, and we will freeze yn, and we will do something trivial in yn direction. We will do Minkowski's inequality in yn, or triangle inequality in yn direction. A x minus y f. So y, let's call it as y prime, and yn dy prime dyn. Okay, cool. So in order to bound the LP normal weight, we use Minkowski's inequality in the last integral. LP and then dyn. Okay, now then we will prove a uniform estimate for every yn, and let's say that we set yn to be 0. Okay, and after setting yn to be 0, step 2 is pseudo-conformal change of variables. Let's look at the phase function. This is our phase function, and for the phase function, what we have now is square root of yn squared plus x prime minus y prime squared. For the for this phase function, need to remember the change of variable we did is we first pull out yn, and then we have a 1 plus. Okay, in order to pull out yn, let's without loss of generality say that yn is comparable to 1. Otherwise, we do a rotation, and then we do the same thing for yn minus 1 or y1 for other variables.
Sorry, Shaoming. Did you mean xn?
Yes.
Did you mean xn instead of yn?
Oh, sorry. Yes. Thanks. Yes, you're right. Xn squared. Xn. That's right. Thanks. We pull out xn, and then we have x prime over xn minus y prime over xn. And later, xn will play the role of t. And xn is about 1. Now, after pulling out xn, we do the change of variables. And this is x prime over xn. Let's call it, for instance, let's call it u, and 1 over xn, let's call it t. And our phase function becomes 1 over t, 1 plus u minus ty. And okay, let's also rename y prime as c. So rename. Square. So this is our new phase function. And what's special about this phase function is, okay, perhaps if we only stare at this form, we may not see immediately that this is the restriction problem. Well, it is not entirely the restriction problem, but let me show you how to view it as. You will agree after doing some simple computation that if we do wave packet decomposition, what we see the properties for all wave packets, we say that they're exactly the same as properties of wave packets for the restriction problem. So let's think of how wave packets look like. How wave packets look like, and to see how wave packets look like, we would like to compute critical points of the phase function, right? And what we do is we take gradient xc and see. So take. So this is psi, psi u t xc. Take gradient of the phase function xc, and this is exactly what is it? It is u minus txc divided by 1 plus u minus txc square. This form is not that important. What's important on the right-hand side is that this term always appears as a whole. This u minus tc term, and let's say that for variable coefficient for Hemander operator, when defining wave packets, right? What we do is that we set it to be say omega naught, and we would like to compute how wave packets look like. And what's important is that if we solve for fixed omega naught, if we solve u and t to get a relation on u and t, we will always see that the relation between u and t is linear. That's because this term u minus txc always appear as a whole, and when we solve this equation, we may not be able to solve it explicitly, but that's not important either, right? We will see that we always get u minus txc is equal to some other function depending on omega naught. And this means wave packets are straight. Okay, and we no longer have any curved wave packets as in the general oscillatory integral satisfying Hemander condition, or well, Bergen's example of Kakia compression doesn't occur here either. Okay, so this is one key observation we made while doing this project is that if we do the pseudo-conformal transformation, we will see that the phase function, we'll see that this phase function, also it doesn't look exactly the same as the phase function of the Fourier extension operator. It is good enough when we define wave packets and all wave packets, they behave in the same way. Actually, there's bi-Lipschitz map between the wave packets here and also the wave packets for the restriction problem. And I think at this moment, experts can already believe that all the tools that have been introduced, for instance, polynomial Wolf axioms and other tools using the wave package decomposition that that has been successfully used in the restriction problem, they should also apply well to the Bochner Riesz problem after doing this simple calculation. Okay, so this is the proof. How much I would like to mention the proof. In the end, let me the last 2 minutes, I would like to say something that I find quite amusing. I think I can say some phenomenon, and it's in parabolic rescaling of this problem. It is okay. Now I would like to carry the lambda parameter and the phase function. Let me write it in this way. It's x minus, I suppose I have sexually changed u to x, t c square. Okay, I have also done some rescaling in x and t variables, and that's why lambda appears here. Okay, so and please accept that this is also our phase function. So for this phase function, initially the relevant range for xt is this, is x and t, is that we can restrict the range of x and t to, this is lambda over 2, this is lambda, this is minus lambda, lambda. So this is irrelevant range of x and t. Okay, why am I saying this? The reason is that in the phase function, t appears in the denominator, and that while working on this project, this is something that always concerned me. And in the initial setup, it's not that bad because t is always large. The shaded part, right? T is always bigger than or equal to lambda over 2. However, if we do parabolic rescaling, and also the range of c is always the, let's say, the unit cube centered at the origin. Parabolic rescaling. If we do parabolic rescaling, that means we do where k is a large parameter. So we do parabolic rescaling, and we will see that, well, that means lambda over 2. Let me quickly do this computation. X minus t c over k square. Okay, and now the change of variable we do in the x is changed to kx, and t is changed to k squared t. And the phase function will become something like this: is lambda over k divided by t, lambda over k square plus x minus t c square. And you see that lambda is replaced by lambda over k. And this is fine. our phase function is still more or less invariant, right? And what's kind of strange to me, or something that I still haven't fully understood, is that this picture, after parabolic rescaling, it becomes this. This is x, and this is t. It is squeezed, and this is lambda over k squared, lambda over k, lambda over k. And this is the relevant region for the x and t parameter. And what always bothers me is that now this t parameter is very small, right? Our phase function is here, and we see now that the range of t, which is lambda over square, can be much smaller compared with our parameter lambda over k. And okay, that's the last thing I would like to mention. And if any expert in the audience has any, if you have seen anything like this, or if you have any idea on what's going on, or help me to get rid of the concerns, that would be great. Okay, Marina, that's everything I would like to talk about.